Hi, I'm Yufei and today I'll present our work, Automatic Recovery of Fine-Grained Compiler Artifacts at the Binary Level. This work is co-authored with Ryan Court and Kevin Snow from Zeropoint Dynamics, and my advisor, Fabian Monrose from UNC Chapel Hill. Our work focuses on identifying the set of individual optimization passes for each function in a binary, with the main motivation of helping developers and analysts to find potentially vulnerable functions caused by compiler optimizations. So today's programs have become increasingly complex, and there are more and more platforms that are getting smarter. In addition to personal computing devices and servers, we also have embedded systems like routers and IoT devices such as smart cars. With more programs and more complex programs, as a security practitioners, you might wonder there's larger attack surfaces and there's higher chance of human errors. We humans often make errors in programming, leaving vulnerable code. Thankfully, the community has developed common secure coding practices to prevent human errors. For example, it is common for programmers that deal with secret data to erase such data after using them, such that even if an information leak happens, the attacker cannot find the secret data. You might wonder, you might think that if you strictly stick to the secure coding practices, your code will be completely safe. You'll write secure C code or C++ code, and then the compiler will faithfully generate binaries that exactly match the designed behavior. However, have you questioned that do the compilers actually faithfully compile all of your code? Do these secure code practices really exist after those optimizations? And the answer is no. Compilers are now heavy optimizers as well. And many of the optimizations could potentially remove the secure coding practices that programmers added. In fact, in a previous work by De Silva et al., they discussed the Correctness-Security Gap, which arises when a compiler optimization preserves the functionality but violates a security guarantee made by formally sound, correct source code. In their work, De Silva et al. Described three types of the Correctness-Security Gap. First, they have compiler optimizations may create side channels where developers of cryptography libraries would add code to prevent constant time, to produce constant time operations. But the optimizations such as common sub-expression elimination and people optimizations may simplify or remove those code into faster code, but not constant time. Second, developers sometimes rely on undefined behaviors to perform protections, such as detecting overflowed signed integers. However, compilers are free to perform whatever they want, or maybe even sometimes identified that such check is unnecessary, because a very large signed integer will obviously be larger than a negative integer, and remove those checks. And finally, we have persistent state violations, where developers would erase secure data or verify the code that deal with secure data. But the compiler would then use either dead store elimination or function inlining optimizations that keep the data available in the memory beyond their design scope. There are some developers that know this issue, the Correctness-Security Gap issue. Experienced developers are applying tricks to trick the compiler to avoid such optimizations. We have examples that use various forms of volatile functions or volatile objects, such that the compilers will not understand that the memory object will not be in use after. However, What works for the current version of the compiler has no guarantee that they will work for a future version. And finding these compiler-induced issues is prohibitively difficult. Developers need to either inspect the entire disassembly of the program or use GCC or another debugger to make sure that the code faithfully performs what they want. So is there an easy button for this problem? That is our focus. So our goal is to build a tool that identifies the sets of optimizations applied to each function of a program. Our tool can help developers detect 2 of the 3 types of the correctness-security gap, the side channels and persistent state violations that happens because of compiler optimizations. To our knowledge, we are the first to focus on the pass-level identification. So a little bit of background on optimizations and passes. Most developers only focus on the optimization level when they compile programs. However, internally, compilers apply fine-grained optimization passes to each optimization level. They run each optimization pass, and the pass will determine whether the optimization is necessary, and if so, modify the code. Here is a high-level overview of the compiler. And our tool focuses on detecting those optimization passes that actually modified the source code during the compilation. For our motivation, we list a few previous work that fits similar goal. We have Origin, Himalaya, and NeuroCI. All of those previous work focus on detecting the coarse grain, the compiler configuration, including the compiler family, compiler version, and the optimization level of a function in a binary. And they all utilize deep learning techniques. However, for our exact purpose, we need finer-grained information. We need to given a binary function, detect the individual optimization passes. And we're also not convinced that we really need deep learning techniques for our techniques. Here is an overview of the state-of-the-art previous work NeuroCI. So taking a binary file, disassemble it into individual functions, then extract features using word2vec into vectors, and then run either a convolutional neural network or a recurrent neural network to determine the compiler configuration for each function. And to verify that, to show that we don't need deep learning technique, we build a classifier that matches this NeuroCI's behavior, but using only simple features and a multi-class decision tree-based light GBM classifier. We only use 7 types of simple features, including opcode instructions, registers, 2 grams of opcode and instructions, and first and last instructions. They are all binary features using one-hot encoding. And we apply feature engineering when selecting the types of features we want. For example, we also tried 3 grams of opcodes and instructions, but eventually decided to not use them because while they could bring single digits of improvement in our results, they take significantly longer time to generate. So after we built our classifier, we were eager to compare with the state-of-the-art on how we do without a deep learning technique. Thankfully, NeuroCI published their dataset, so we used the same dataset that includes 15 programs, 5 compiler versions, and 3 optimization levels. While going through the dataset, we realized that it is not really balanced, so some classes have significantly more functions than others. So we applied dataset balance. Just like NeurCI, we split the data set into 80% training set and 20% testing set. First, we reproduced the results of NeurCI and verified that their results closely resembled their claimed result in their paper. We show the confusion matrix of the results. On the x-axis is what NeurCI predicted, and the y-axis is the actual configuration. So even with the balanced data set, NeurCI still performs very well. It is mostly confused when dealing with Clang 3.8 and Clang 5.0, where it misclassifies many of the functions for the compiler version. And similarly, it is confused when detecting GCC 6 versus GCC 4 functions at O0. Next, we show the result of our own approach that utilizes shadow learning and simple features. On average, we have a slightly higher F1 score comparing to the state-of-the-art. Just like NeurCI, our approach also shows that it cannot accurately identify Clang 3.8 and Clang 5.0 functions. We have shown that with well-engineered features, a shallow learning technique could do just as well in the configuration identification problem. Now let's switch to the more complicated problem, the optimization path identification. So while going over existing work, we were surprised that nobody had looked into this problem before. Even the ones that do mention the problem claim that they will be very challenging to detect. This is a quote from a previous work, that some flags would be challenging if not impossible to detect, the dead code elimination flag being one example. However, we disagree. But before building our model, we first need to generate the data set of the compiler passes, because compilers run passes internally, and we couldn't retrieve the pass information at a function level. Therefore, we modified the legacy pass manager of the LLVM compiler infrastructure to generate our ground truth. After generating our data set, we then modified our existing compiler configuration classifier to classify the fine-grained compiler pass information. First, we modified our single light GBM classifier into a multi-label classifier that includes a light GBM model for each compiler pass. And we also added optional support for dynamic feature generator, where we utilize a symbolic execution tool and force execute every function to extract the registered deltas. So since we had to extract additional information from the compiler, we used a different data set to evaluate our compiler pass identification. We used 4 popular open source projects, BingUtils, CoreUtils, HTTPD, and SQLite. We utilized the Clang 14 compiler and modified its legacy pass manager. And we compiled the 4 projects using 4 optimization levels from O0 to O3. In total, we extracted 83 compiler passes that are applied to functions, but not all functions. So we excluded the compiler passes that are applied to every function in our data set, because that's very obviously easy to detect. They're just always present. And in total, we generated 552 binaries and about 150,000 functions. Just like our compiler configuration evaluation, we also balanced the data set such that for each pass, for each compiler pass, our data set have the same number of functions that have the pass and the number of functions that do not have the pass. We split our data set to 75% training set and 25% testing set. So the average F1 score across all 83 passes is 92.1%. And here we listed the result for the dead code elimination passes. Contrary to the quote from previous work, our model could detect these dead code elimination passes with high F1 score. They're all higher than 83%. And more importantly, thanks to our shallow learning model, we could interpret the results to see exactly why it performs well. Here we show the top features for the pass aggressive dead code elimination. We chose this pass because it is one of the dead code elimination passes, and its code comment in the LLVM source code is clear on what it does. So it removes dead code, especially in loops. And we could support the claim, seeing that our classifier found four of the top features are compare instructions that are common in loops. This shows that our classifier picked up the behavior of the pass itself. However, in addition to that, our classifier also picked up the behavior of other optimizations. For example, the number one feature here is actually the frame pointer setup, where at 01 or higher optimization level, the compiler would just skip the frame pointer. And similarly, the classifier also picked up various no-op instructions that are used for alignments that also appear at a 1 or higher optimization level. Furthermore, even though the aggressive dead code elimination pass is applied at the intermediate representation level before register allocation, our classifier still picked up several registers among the top features, showing that its relationship, this pass also has a relationship to the machine level optimizations. So in summary, we discovered that our pass worked well by identifying both the pass's own behavior and its relationship with other passes. In addition to dead code elimination, our classifier also achieved high F1 score on all the compiler optimizations that are described in the De Silva et al. Correctness-Security Gap, claimed to be having an impact on security, including code motion, tail call elimination, common subexpression elimination, strength reduction, and people optimizations. For all of these passes, our classifier achieved an F1 score higher than 83%. And finally, since our main motivation is to help developers and analysts detect potential issues in their code induced by compilers, we ran case studies to show that our tool can assist developers in real world. So we applied our tool to BusyBox, the latest version of BusyBox at the time of experiment. BusyBox is a popular Unix utility suite for embedded systems. And our classifier detected that these function in the SHA encryption was modified by the dead store elimination pass. And in fact, the developers specifically mentioned in the code comment that they want to erase the intermediate values, such that people attaching to processes or reading core dumps cannot get any information. However, the compiler kicked in and applied dead store elimination, which completely removed these erasures. We have found this issue and reported the bug on the bug tracker of BusyBox. Next, we also found an issue in Apache HTTPD's support utility program htpassword, where the compiler just simply removed the erasure instruction that erases the plain text password. So after this get password function executes, we were still able to recover the entire plain text password because the code that erases the password is gone. And the same with Crypto++, which is a cryptography library. Our classifier detected the dead store elimination pass at O3 optimization for the CAS256 encryption function, where the developers erases the intermediate result inside the variable kappa, but the compiler removed this erasure. Our next step is to conduct a large-scale evaluation of the compiler correctness-security gap across platforms, including both Linux programs and popular Windows programs. And we have already found a number of new problems due to compiler optimizations. To conclude, compilers can nullify secured code practices added by programmers, and it is very challenging for developers to detect that their code is undermined by the compilers. And we applied shadow learning to build a model that identifies compiler passes applied to each function of a binary to assist developers and analysts to better handle this problem. Thank you.